Good morning all. Okay, so this video is going to be about momentum and the conservation of momentum. So I've taken the 5 pages of notes that I have placed on Compass for you and tried to do a quick summary into one board. So there's going to be a fair bit of me talking, and then I'm going to go through some of the examples that I have in the notes with you on the board, just to explain it in a bit more detail. So momentum. I think if you stop and think about it, you'll kind of understand what momentum is. So it relates to an object's mass, but also their speed. So if I walk down the street, I will have a certain momentum. If I run down the street, I will have a much greater momentum compared to when I'm walking. If my daughter, who's only 9, very small, and I jog down the street and we stay together, so we have the same velocity, I will have a greater momentum because my mass is much bigger. If you kind of think about it in a way, it would require more energy for me to jog down the street than it would for her. So it's kind of related to this idea of momentum. So we're talking about mass and also velocity. All right, now momentum is represented by the letter P, smaller case p, in formulas. And so therefore momentum is equal to mass times velocity. If you think about it, force is equal to mass times acceleration. So we've got something sort of similar there. So momentum is mass times the velocity of the object. All right, very simple formula. We can do a really quick calculation about calculating something's momentum. So example number 1, if we've got a 60 kilogram student and they're moving at 3.5 meters per second to the east, what will be their momentum? We know that P equals mv. We've got a mass of 60 kilos. We multiply that mass by 3.5. So we get a momentum of 210 kilograms meters per second to the -1 to the east. So momentum is a vector and does require a direction as well as a magnitude. All right. That's a fairly simple, straightforward calculation. It's a fairly simple formula for that one. That's when we just want to know about momentum. Now, there's a few other things that we are going to look at. All right, so force is equal, because we want to be able to associate force with momentum. So force is equal to the rate of change in momentum. So if you have your final momentum minus your initial momentum divided by the change in time, you will be able to get net force. So that's how force and momentum are related to each other. Change in momentum over the time change will give you net force. Okay, now in the notes you'll see that there's a your turn question, so you guys can work through that. The next thing I want to talk to you about is the conservation of momentum. Now in some questions, remember momentum is conserved. So the amount of momentum at the start or before a collision occurs is going to be the same at the end. Later we're going to look at what happens when momentum is transformed into other forms of energy, but right now we're just going to focus on this idea of momentum being conserved. So the total amount of energy before a collision has to equal the total amount of momentum after a collision. Alright, so basically if two objects are colliding in one dimension, we use this formula. It's m1 multiplied by u1 plus m2 multiplied by u2 will equal m1 v1 plus m2 v2, where you've got the mass and the initial momentum of velocity, the mass and the initial velocity of both objects involved in the collision is going to have to equal the mass and velocity of both objects after the collision. Alright, so this takes us into our second example. A 2.5 mass is moving at 4 meters per second west towards a 1.5 kilogram mass moving at 3 meters per second east. So they're traveling like this. They're coming towards each other at different speeds. Calculate the final velocity of the 2.5 kilogram mass if the 1.5 kilogram mass rebounds at 5.0 meters per second. So the 1.5 was traveling at 3 point, it's had the collision and it's rebounded and it's moving faster. Okay? So the first step in the question is to write down what we have. So the mass of object 1 is 2.5, the initial velocity of object 1 is 4.5, but because of its direction, we're going to resolve that by using a negative, so it's going to be negative 4.5. V1 is what we actually want to find out. The mass of object 2 is 1.5. It's initially traveling at 3 meters per second to the east. After the collision, it's traveling at 5 meters per second to the west. And we resolve the west direction by making it a negative. We put that into our formula. And we're wanting to solve for V1. So we end up with 2.5 multiplied by V1 is equal to negative 11.25 plus 4.5 minus negative 7.5. So V1 is equal to 0.75 divided by 2.5. So the V1 is equal to 0.30 meters per second to the negative 1 to the east. Okay, you can follow that process through carefully in the notes that I've given you. So in this is an example where the initial velocity, the initial momentum is equal to the final momentum. Some of the velocities have changed, and that's what our calculations are sort of working through to find out usually what those change in velocities are. Alright, there's also a your turn question here. These formulas are fairly straightforward if you just stop and think about them. They're pretty easy to use. Now, momentum can happen in a few different ways. In this case, we had two objects traveling in different directions. They collided, they rebounded off each other. So we had two objects at the start and two objects at the end. And what changed was the velocity that they were traveling at. In some instances, you can have momentum where when the objects come together, they get stuck. So you have two objects to start with, they come together, they get stuck, and you end up with one object at the end. So we need to make a little adjustment in our formula. So we have the mass of the first object and the initial velocity. We have the mass of the second object and the initial velocity. And then we have the mass of the combined and the velocity of the combined. Okay? So that's how we make a change in the formula. The other kind of question that you can get is where you might have one object and that object explodes and you end up with two objects. Okay? So in that instance, again, we would adjust the formula by saying the mass and velocity of the first object is equal to the mass and velocity of the two other objects. that it's now been exploded into. Alright, so I'm going to give you an example of the first case where they collide and they stick together. Alright, so when masses combine, so we have object 1, object 2, and they're going to combine to create object 3. So a 5 kilogram lump of clay is moving at 2 meters per second west towards a 7.5 kilogram mass of clay moving at 3 meters per second to the east. They collide and form a single mass, and we want to calculate the final velocity of the combined clay. Now, none of the clay got lost, so we know what the mass is going to be of the final combined. Okay, so I've got 5 multiplied by -2 because my 2 to the west becomes a negative, plus 7.5 times 3 has to equal 12.5. That's the combined weight, and the V3 is what we're trying to find out in this instance. So the V3 is equal to 10 plus 22.5 divided by 12.5. So the V3 is equal to 1 meter per second to the east. And you'll be able to follow that example through more carefully in the notes that I've given you. In the notes, you'll also find that there's a question relating to when you have one object and it explodes and becomes 2, but I'm pretty sure from what we've already done, you should be able to manage to work that out. If you have a look at the formula, it's pretty straightforward. Alright, so after watching this, please go and do the questions in 10.4 review and see how you go. See you later, guys.